we don't have one in our solar system that we know of. And so as a result, we do know we have spectra and things to compare to for lots of planets that are in our solar system, but we don't have any spectra, at least not in our own solar system, of mini Neptunes to consider. So enter the efficient atmosphere model, equilibrium searching and assessment. This is a project worked with Ty and Jonathan. And this is going to have just a quick crash course in atmospheres. If we would take just the simplest case where you have a not so scaled sun and have it, all the energy going in is equal to all the energy going out, which is intuitive, right? Because if we were keeping too much, and we would just get hotter and hotter, and if we lost it, we would be getting colder and colder. So we start with at least considering the simplest case of equilibrium here. Of course, it's a little bit more complicated than that, and we can also consider that sunlight that's coming in, there's heat that's internal to the planet, and you have heat that's rising, and as it rises, it convects, just like if you have a convection oven or microwave, it moves air around to transfer heat. And then at some point, the air gets thin enough to where radiation can become the dominant form of heat transfer again, and that point we call a radiative convective boundary. So this is an example output from the model that we're using. Let's see, your right, is a spectra, sample spectra with, again, the wavelength in microns and the intensity on the y-axis. And on the left there is a pressure temperature diagram. And so why do we care about these pressure temperature diagrams? It's if you have, on our x-axis, you have the temperature and the pressure, or you can think of it as altitude on the y-axis. This line tells us where it's in equilibrium, where it's in balance between the pressure and the temperature. So we would like to know, first off, where there can actually be liquid water, because this is what we're looking for considering habitability. But also we do like to know what an equilibrium looks like paired with a spectra, and maybe if we see things that aren't matching the spectra, then it might not be an equilibrium. That might give us a clue. The thick part of this line is that convective region, and the thin part is the radiative part. And the point where they meet is that radiative convective zone. So what does this searching look like? If you start with a reasonable guess for where this radiative convective boundary might be, and we have, say, we'll call it 68 layers for an atmosphere, just to choose a number, then the algorithm will search around and find something that is hopefully in equilibrium. And so this is showing all different levels, including some really terrible guesses to start with, and where it ends up in equilibrium. And we'll talk about what the colors mean in just a moment. So the first novel approach to this is doing this all in parallel. So instead of running these one after another, where maybe it takes an hour to run something with a moderate initial guess, where we're searching for a solution. So in serial, if you really wanted to do all 66 because you wanted to test every single one, you could take upwards of 66 hours. In parallel, it takes about 68 seconds on average. We don't have to use quite as many cores because a number of them solve quickly. And compute time on the wall clock reduces down to about an hour and a quarter, which is a lot more manageable. It does take 60 cores. Enter NAU's Monsoon, shown here with Chris Coffey protecting his servers. It's a 102 teraflop, which means that trillions of floating point operations per second, 3,000 processors, some GPUs, and a bunch of RAM and storage. Importantly, these machines are connected quickly with each other. It's important for our project, and we're on this 10 gigabit pipe that happens to also be where the archive is that we're working with is sitting on. So now approach 2 is you can imagine that if you have 66 or even 3 or even 2 solutions come out of the other end of running this model, how do you pick the one that actually is best? So this is why we came up with 2 different quality metrics. There's an energy conservation metric, so this is just making sure that no energy is treated or destroyed. And then pressure temperature equilibrium. So again, at every level, making sure that it's physically realistic. And so at every level, we also have a guarantee for both of those metrics that if it dips below a 90% error, where this color bar is showing 0 to 1 as the quality, so if it dips, not 90% error, but it dips below 90% quality, then we flag that model as rejected. So in this particular plot, those dashed lines are the ones that had at least one level that exceeded that error threshold or went below the quality threshold. But you can imagine that if you just averaged it, it might look okay, but you could have individual levels that are not okay. So some initial results with 600 mini Neptune spectra and pressure temperature profiles. We've come up with these novel approaches to the computation, and we have these new quality metrics. Next steps will be to extend this with a mod to high-resolution spectra, and use those to characterize the emission sensitivities, falling back on that plot we saw before of the instruments. So, okay, on to project number 2, active asteroids. So this is not a comet you're looking at. This is an asteroid, P2013 R3, and it's this is from Jewett et al. 2017, and it's showing there's a blow up in that section where you can see pieces of the comet that are in there. That's each part is labeled A through D, and there's a couple arrows pointing away from the sun, which is also where you see that tail pointing. So what makes them active, you might ask? There are a bunch of different possibilities for activity. This is 67P, which is a comet, but it shows nicely some outgassing because we sent a spacecraft there. And we have sublimation of volatiles is one possibility here. We also have impact. It's not impossible at all for things to hit each other. We've seen that several times. This is an art expression of Pallas being hit by something, another object. Thermal fracture is another possibility where you have an object. In this case, this is Phaethon is really the one that is labeled as having this mechanism right now. Phaethon is the one it's an asteroid that's the parent to the Geminid meteor shower. It's thought to be. And so the idea is that if it goes around, that it can crack open from the expansion due to heat and either expose volatiles or actually cleave off entirely and give you some debris that way. And then for the one that I just showed you a picture of, it's thought that probably this is rotational breakup, where for dynamic and physical reasons, the thing ends up spinning faster and faster to the point it can't hold itself together anymore. And that depends on the strength of that body. So what's the motivation again for these active asteroids? Why do we care? They describe the distribution of water in our solar system. I mean, they can tell us about where some of this water is. And that's an important way to know where we could maybe explain where some of the water on Earth came from. It's a great starting point to know where it is now if you would like to work backwards and figure out where it came from. It could also inform us about a potential water resource. A colloquium last year at Lowell about asteroid mining, but they can be used for other purposes as well. People also care about understanding their content so that they can do things about making sure we can deflect one if time becomes. There are a bunch of challenges though, I mean not the least of which is that there's about 20 known active asteroids, so they're not really well understood. And there are many asteroids, so it's the proverbial needle in the haystack. And so they're also very faint. The activity can be even fainter, and so it's even more difficult to detect. So enter Safari, searching asteroids for activity revealing indicators. This is published in PASP. This is work I did with Anthony Curtis, Michael Mulmert, Scott Shepard, and Chad Trujillo. We used the dark energy camera. So this is on the Blanco 4-meter telescope at Cerro Inter-American Observatory in Chile. It can see exceptionally faint objects in a very large field of view. It has 62 chips. They give it 520 megapixels. And those 62 chips are important because you can see that pattern there. It's both on this image of the camera itself, as well as here in this upper left. So we started by splitting each chip apart into its own image file. We then did analysis on each one to determine the coordinates that they resided in really accurately. We located the asteroids that were within these. We extracted thumbnails of those asteroids. And then finally, we enhanced the image using our own image techniques. The previous parts of this were the photometry pipeline from Michael Momert. The last step was to extract, to do a bunch of different color profiles as well as image smoothing, mostly to make it easier on the humans that were actually looking at these objects. So this is what we looked at. Each of a few of us looked at 16,000 different thumbnails. Yeah, this is not looping. There's quite a few of them. So the asteroid's always at the center. The grid is just to sort of help us to pinpoint where things are, to visualize it. It's quite a few objects, and as you might imagine, it could be a bit challenging to look through all of these. This actually goes for a while, even at this frame rate, so we're going to move on. There were a bunch of challenges that came out. Just one example was false positive, things that were very misleading. I certainly thought that I had found active asteroids when I had not. This one shows several of the challenges in one frame, where the actual object is at the center of the asteroid that we're considering. There's a lens flare or scattered light that's coming from a brighter object, and you can tell that this sort of looks kind of like it could be a tail, especially if that brighter object was cut off. Background galaxies, there turn out to be a lot of galaxies, and so we see a lot of those in our fields. Cosmic rays, especially with some of these longer exposures, that's D up there, that line that's connecting to it. These are image artifacts that end up sometimes coinciding with the object in the center, and then E there is a bunch of coincident objects or blended objects, which can, when you have enough of these, start to line up and look like a tail. So this is important that we have this understanding, because this is going to inform a section of our project that we're doing later. So some initial results, there were 12,000 asteroids that we imaged, unique asteroids. Like I said, 16,000 thumbnails. We constrained the occurrence rate to about 1 in 4,000, and we documented a bunch of false positive scenarios for citizen science to talk about in a moment. There were 3 previously observed active asteroids. These are ones that are already known to be active. One with visible activity. So I'm not sure if you can see the tail or not. This is always fun to ask people if they can see it, but there's some lines to help out there. So the next stage of this project, Safari 2, is going to involve citizen science. This is with undergraduate Jay Quay I'm working with, plus several committee members being drafted, and superhuman citizen scientists, we hope, as well. And this was what I proposed for with a GRFP as well, that was funded. Challenges. So first off, it is big data. We're talking about extending what we did with Safari to the entire NOAA public archive. The image data by itself is 250 terabytes, strongly compressed. And so it's a large data volume. There are call limits. We can't just check with all of these services about the positions of the acids. That was Courtney's media Courtney. Yeah, I think something fell. Right, call limits. Yes, it looks like a hack if you try to submit 30 million different queries at one time. It definitely looks like, well, you are overwhelming them if you do that. There's also archive limitations, so every archive seems to be different, and in this case they have a limit on how many you can get in for a query at a time, how many search results you get, as well as the mechanisms for downloading. Heterogeneous input. So we're matching a lot of disparate sources. This means different file formats, different conventions for different parameters, which is hard. Complex naming system. I've been running a little analysis. I have so far there's 3 objects that have 20 different designations. This just happens when asteroids are found at different times, and then later somebody pieces them back together. But because some of the matching we're doing is with literature sources like families, it has to be based on the names that they're associated with, so that can be a little bit challenging. Mutable resources. So everything that we're using underneath here is also continuously changing. I mean, the services that tell us about where asteroids are, they're constantly improving their systems. Like as more observations come in, they can constrain them better. The archives, of course, are growing, so as data is released and becomes public, it's also growing. And the tools change, not just the software that we're using, but also the data even within the archive has changed over time because they have improved their pipeline and some of the tools that they have. This plot is just showing the growth of the Deckham Public Archive since its first month in 2012 all the way through its the 70th month, where it flattens out just because there is nothing released yet. So some initial results, we've already been doing a lot of work on this. We've already managed to ingest the entire database that we need. We have Monsoon already configured and designed a SQL database, which is for storing all the information. And we've finished the catalog matching overwhelmingly. The name resolution has been sorted out once and for all. There's a function now to also download by name, which we've been using for testing. So if anybody has an object they're interested in, just tell me the name and I can tell you where all the files are. I can send you a list of something, you can just press a button and download them all at once. In progress, so population analysis is still going on. We're still analyzing the whole set. The comparison fields are going to be for citizen science, which we'll talk about in a second. And the citizen science project is being developed. Here's just a result from the analysis that we're doing. So this is, these are 1 degree square bins that we were looking to count how many observations we have of an asteroid. So in each bin we have up to like 10,000 or more asteroids in one bin. It's an interesting looking plot. There's some interesting features on this plot. They're still trying to work out. It's just a latitude and longitude plot in degrees. On the side, there are 30 million asteroids in this image. So the citizen science part is the next part of the undertaking. This is not a small undertaking. This involves crowdsourcing scientific activity to public. So it doesn't require extremely specialized skills, but we are going to ask them to look for tails and coma, or the halos, around asteroids. Input will probably be around 20 million asteroid thumbnails and 20 million comparison thumbnails. So the purpose of the comparison thumbnail is because there are so many galaxies and other objects that can coincide with the asteroid. We would like them to be able to compare an identical region at a different time and see if that thing is still there, because the asteroid should have moved on, whereas an artifact, galaxy people, a galaxy should still be there. We hope to get hundreds of active asteroids, new active asteroids out of the project. It should be enabling the first large population study. We hope to engage some tens to hundreds of thousands of citizen scientists, and then produce a machine learning training set to hopefully automate some of this for future large-scale surveys that are coming online. So in summary, again, explain atmospheres. We want to model these things so that we can explore mini-Neptune climates until Chad finds one. We don't have one we know of in our solar system, and so we would like to know what those spectra look like and what the features are of these climates. And we want to know what we're going to need to be able to actually detect these things, especially detect water, to look for life with the current and especially the upcoming and proposed telescope missions. For active asteroids, next step is deploying a citizen science project to help understand the distribution of water in the solar system, produce a machine learning classification set, and to engage citizen scientists in real, meaningful, and accessible science. So with that, I have questions, but I would like to leave an acknowledgement slide up here. Thank you very much.
Okay, we have time for a couple questions, and again, if you need to leave, remember, there's a door in the back. Questions? Oriel?
On the image of the square degrees of the sky, so are these coordinates like celestial sphere, like projected to space? So,
But it's not, I mean, it's, there's no, it's not like a Mercator projection or something. This is just a XY grid, latitude and longitude.
So, can you explain what some of the more prominent features are?
That's a good question. So, I would say the absence of objects here is the Milky Way, which generally you don't want to point a really deep probing telescope, or, I mean, it just would overwhelm it. Although there's definitely some observation that's taking place in some of it. If you were referring to like the horizontal lines at 20 and 0, I'm not sure. I redid this with only instrument data to make sure there was no calibration data in here at all. No darks or flats or biases or anything. Well, they don't do darks, but for people that know the observation process, and it's not that. So it is a great question as to why those are there. You notice that the range is not the full range because it is a southern hemisphere telescope. So usually you'll see too much going above 20 there, except for at 20, and then goes down to about minus 80. And so at this point too, there's 1 pixel is 1 square degree, and since the telescope has a large field of view, you can start to see sort of individual pointings, like this is a track of pointing.
Is the big band just the ecliptic?
Yes.
Other questions for Colin?
How do you plan to deploy your citizen project and get people to actually interact with it and do it?
That is a fair question. It could be a very long answer, but I will just say that it's this is through the Zooniverse platform. I've talked to some folks at Zooniverse already, and so with Jay, we're preparing different tutorials and training videos and components to help with that process. It's a pretty well explored platform. They've done a lot of projects already. The very first project had like 10,000 classifications an hour within 24 hours of launch. So they, there's a series of stages. Once it's actually ready to be launched though, there's like a 5 to 6 month window of review from their panel. They have about 70 scientists on the panel. Interesting. Yeah, so that it's definitely a stage process. There will be a media plan. I'm going to be drafting some people to help me out with some testing, and I can definitely tell you about more, but I don't want to go on too long about that.
Excuse me. You talk about like outgassing. You mentioned it a little bit. But, the type of outgassing that is. 1, what is that? And 2, are there different kinds of like outgassing that you can like differentiate, or like different processes that would cause sort of different things?
Yeah, so there's definitely different processes involved. I mentioned just a few of them. Where is this one here? They're all blank. Well, I mentioned like rotational breakup and thermal fracture.
Each of those can cause a different type of.
Each one can.
Okay, right.
Depends on which bands you're looking in. You might be able to discern between ice and dust, but to say exactly what it is, like if it's what volatile is sublimating, is a good question. We do have spectra for a number. Like we know that there's water on 24th Themis as water ice, although we've never seen any come off the surface, so we don't know. It's not an active asteroid. But like Rivkin and Emery talked about that. So yeah, if we know it through its spectra ahead of time, that would certainly help. Otherwise, it will be, if we see recurrent activity, like if we see activity that happens over and over when it's like closest to the sun, that's a good indicator that it's a sublimation of volatiles. It would probably be unlikely that it would have a collision at exactly the same place every year.
Sure.
Or every its years.
Thanks.
Mark, you had a question?
Yeah, it's kind of related to that. So, is this project what you're doing, are you looking at compositional information for the outgassing, or when you see an active comet, are you just looking for tails and things? And that's
Yeah,
about it?
just looking for tails to start with, and then when we have some, to try to work out, especially to see it recurrent, if we can see it is something that's sublimating, then we can consider doing more with it. But at first, just looking for activity.
So you're using Monsoon, and it said it had something like 200 terabytes of storage, and then you also mentioned that just the compressed data files are 250 terabytes. Assuming you want to do more than just have the compressed data, how do you deal with that?
That's a fair question. And we can't have the data. We can only have a transient copy of the data. So we have to know ahead of time everything that we need from every file when we download it. And we have to be very, I've spoken with Chris Coffey about it. It's not like this is going to blindside him. But yeah, they do have a petabyte and a half of total storage. But for those of us on the list that routinely get emails saying, please clear out space, we know that there's not that much space free. So it is definitely going to have to be done in stages. I'm also not going to be doing this chip by chip extraction. I'm going to try to do the whole field at once as a mosaic, which will mean that we don't have to double, triple our space requirements. So before, to extract those chips, you can imagine if you had 62 chips and then you make 62 separate files of those chips, you've now doubled your space. Also, a lot of the utilities don't work with compressed images. I've written my own pipeline from scratch this time, and it's going to work with compressed files. So it's going to be tough to work around. We know that the result data is not going to be small. Thankfully, we have unlimited storage with Google through NAU, which I am putting to the test because I think I'm up to 20 terabytes up there, and it's that's where at least the backup is going to go. I mean, data management's always on my mind, and backup is important too.
Okay, I think that's a good pausing point, so if people do need to leave, call it the end of Q&A. If you do have some more questions, you can come down front and ask Colin, but make sure everyone can get to their next things. Go ahead.
Thanks for coming.